Hello again. Today we're going to be talking about parametric equations. We're starting an entire unit on using parametric equations with calculus, but today we're just going to talk about what parametric equations are. What they are is a set of equations where instead of y being expressed in terms of x or x being expressed in terms of y, we introduce a third variable t, and now x and y are expressed in terms of this new variable t. X and y are now both dependent on t, and t becomes the most independent variable in the question. So what we have to do is we have to write down two equations, one that says x equals something in terms of t and one that says y equals something in terms of t, and then we have to put a domain restriction on t because it is now the new independent variable. We can also write this as a vector with our x expression coming first and our y expression coming second, but we still list the restriction on the domain for t. When we're graphing these, we're only graphing the x and the y part of these. But we have to keep in mind that we have a restriction for t, and we have to keep in mind that t is what keeps going from -2 to +2. So we need to show that on the graph. I'm going to list various values for t within the restricted domain, and I kind of space them evenly apart. And then based on those values of t, I calculate x according to its formula and y according to its formula, and that gives me 5 ordered pairs that I can plot on a graph. Once I've finished plotting those points on the graph, I can join them with a curve, but I have to keep in mind I have to join the points in the order that they appear in the table, and then I will also draw arrowheads on the curve so that you can see the direction of the particle as it's moving along that curve. Now, if ever I want to eliminate the parameter t and go back to a function in terms of just x and y, that's a relatively simple thing to do. What I do is I simply solve one of the equations for x or for y, whichever one is the easiest one to do. I'll solve that for t, and then I will plug in this new expression for t into the equation that I haven't used yet. And then when I simplify that, that will just be a function in terms of x and y. So for example, using the one that I've already talked about, the easiest of those two to solve for t is going to be the y equation because I simply need to divide by -2 on both sides. So when I do that, I get t equals -1/2 y, and that gets plugged into the x equation. So x becomes -1/2 y squared plus 1. And if I simplify that, I get that x equals 1/4 y squared plus 1, which is exactly what that curve looked like in the previous slide. If I see sine and cosine functions in our definitions of x and y, then there's a different strategy I have to use. What I'm going to do instead is I'm going to solve each of them, one of them for sine t and one of them for cosine t, whichever one appears in that equation. And I will substitute whatever sine t is and whatever cosine t is into the identity sine squared of t plus cosine squared of t equals 1. That's a statement that's always true, so I can plug in whatever I got for sine t and whatever I got for cosine t into that. So let's say I have a different example, and x equals 4 times the cosine of t and y equals 3 times the sine of t as t goes from 0 to 2 pi. Well, if I solve the first one, the x equation for cosine t, I get that cosine t equals x over 4. And the y equation, if I divide by 3 on both sides, I get that the sine of t equals y over 3. Now I plug those into sine squared t plus cosine squared t equals 1, and I get x over 4 squared plus y over 3 squared equals 1. And if I simplify that, I get x squared over 16 plus y squared over 9 equals 1. That's actually an ellipse, something that I couldn't do with just an x and a y. If I had x equals something or y equals something, I wouldn't be able to do that with a normal function like that. So why do we use parametric equations? Well, sometimes we might not just want to know where a particle is along its path, but we might want to know when it gets to each of the points on the path. So let's just look at an example of this. There's two linear functions graphed on this graph right here, and you'll notice that they intersect at the point 8 and 2. I've written the equations for each of those parametrics off to the side there. The green one matches the green line and the orange one matches the orange line. So they do meet at 8 and 2. And so it looks like if one particle was traveling along each of those paths, they would collide at 8 and 2. But if I do some algebra, I can figure out that the particle on the green path will cross that point 8 and 2 when t equals 1, or at the 1 second mark. And the other one will pass through that same point when t equals 4, so at the 4 second mark. They go through that point at different times. So they actually don't collide. Another reason that we would use parametric equations is because, as you saw before, we can use them to represent relations that are not functions. So this example here, if I have x and y expressed like this, I can actually plot a bunch of points using those formulas and get another ellipse, which is not a function even though it is a relation. All right, so here's an application problem. Let's say I have a boy tossing a ball off the top of a 100-foot building with a velocity of 5 feet per second at an angle of 75 degrees. So here's my 100-foot building, and there's the boy standing on top. He is throwing the ball upward at 5 feet per second at an angle of 75 degrees. A man is standing 2 feet in front of the base of the building directly underneath the path of the ball. And if the man wasn't there, what time would the ball hit the ground? Secondly, will the ball actually hit the man in the head? So let's figure out the first question, when the ball will hit the ground. Now, for every falling object, there is a set of parametric equations to model this. If I know the initial velocity, and I know the initial height, and I know the initial angle, then the parametric equations look like this. X equals the initial velocity times the cosine of the initial angle times t, and y equals the initial height plus the initial velocity times the sine of the initial angle times t minus 16t squared. Now that's if we're dealing with feet and seconds, which we actually are in this problem. So here are the parametric equations for this particular question. I'm going to plug in all the information that I was given and get those equations. Now I need to know when the ball will hit the ground. Well, that happens when the y value is 0. So all I have to do is take my y equation and set y equal to 0 and solve. If I do that, I do get a negative value, but I'm not interested in that because time starts at 0. So the only positive value that makes sense is 2.655 seconds. For the second part, I need to know if the ball is going to hit the man in the head. So I'm going to look at what time the ball is horizontally 2 feet from the building so that it's directly above the man's head. So I take my x equation and I set x equal to 2, and that happens at 1.545 seconds. Now that I know what time the ball is directly above his head, I need to know whether it's actually on his head or higher than that. So I'm going to find the y value for this particular time, this 1.545 seconds. So I plug in that t value into my y equation and I simplify it to get 63.807 feet. Well, the man is not that tall, so the ball is not going to hit him in the head. So that's just one application problem for using parametric equations. We will continue our unit on this and get into the calculus of parametric equations, but if you have any questions for now, please let me know, and I will see you tomorrow.